Hello everyone, my name is Vijay Kumar and we are studying power engineering. In the last lecture, I explained about the introduction to hydraulic turbine. In that lecture, we have studied about the various type of heads. Then we have studied about the various type of efficiencies in hydraulic turbine. Now, in this lecture, we will see the generalized equation of energy transfer in rotodynamic machine, or specifically if I say, that is Euler equation. Okay, so in this video we will study about the Euler equation. Let's start the topic. You know very well this diagram. In the lecture of impulse steam turbine, I explained this diagram, and during the lecture of impact of jet on a moving unsymmetrical curved vane, this diagram I explained. You see here, you know very well this one is the blade and u is the linear velocity of moving blade. V1 is the absolute velocity of fluid entering into the blade. You see here I have written steam, you can say fluid also. And V2 is the absolute velocity of fluid or steam leaving the moving blade. VW1 velocity of wheel at the entrance of moving blade. VW1 is the horizontal component of V1. Okay. Now what is the V2? V2 is the velocity of wheel at the exit of the moving blade. So horizontal component of V2, this one is the V2, and the horizontal component of V2 is VW2. So this is the wheel component at the exit of the blade. VF1 velocity of flow at the entrance of moving blade. VF1 is the perpendicular component of V1. Similarly, VF2 is the velocity of flow at the exit of a moving blade. Okay, so VF1 and VF2 are perpendicular to the U, or we can say it is the perpendicular component of V2. It is the perpendicular component of V2. What is VR1? VR1 is the relative velocity of steam or fluid to moving blade at the entrance. VR2 relative velocity of steam to moving blade at the exit. Alpha 1 is the nozzle angle. Alpha 2 is the angle which the discharge steam or fluid makes with the tangent of wheel at the exit of a moving blade. Beta 1 is the entrance angle of moving blade or inlet blade angle, you can say. B2 is the outlet blade angle or exit blade angle. Okay, you see this diagram, and I have explained this diagram so many times. Now let's see the energy transfer in fluid machine, and you know, with the help of this diagram, these are the velocity triangles. With the help of these velocity triangles, I explained about the blade work or diagram work. This equation you know very well. This one is the force acting on the jet by the vane. This is the force acting on the jet by the vane. And if I have to calculate the force on the vane by the jet, then it will be the negative of this one. So we got mass flow rate into VW1 plus VW2. This is the force on the vane by the jet. Okay. Similarly, for using the outlet velocity triangle, if the outlet velocity conditions change like this, you see here in this case alpha 2 is greater than 90 and in this case alpha 2 is less than 90. So if this condition change, then we got the force on the vane by the jet will be this one. Okay, so in general, if we write the force on the vane by the jet, then we can write mass flow rate into VW1 plus minus VW2. I think it is clear. So many times I have explained this equation. Okay, and if I have to calculate the power developed or work done per second, if I have to calculate the power developed or work done per second, then what I will do, I will multiply this force with the velocity of blade. So this is the force on the vane by the jet into velocity of vane. So I can write this one m dot into delta VW into u. This is the diagram work or blading work. I have explained this derivation in my previous videos. Okay. Now you have to remember here I've already explained this thing. Once again, I am telling you that VW1 is the horizontal component of V1, VF1 is the vertical component of V1. Okay. Similarly, at the outlet condition, VW2 is the horizontal component of V2 and VF2 is the vertical component of V2. Now, you see here, this is a general diagram. Now, in this case, there is no blade. In this case, we are assuming that this is a rotor. This one is a rotor and this one is the shaft. Suppose this is the inlet condition and this one is the outlet condition. At the inlet condition, suppose V1, absolute velocity is V1. Now in this case, you have to see very carefully that the three component of velocity, that is VW1, VA1 and VF1. VA1 is the axial component of velocity that is parallel to the shaft. This one is the parallel to the shaft. VF1 is the flow velocity component and it is perpendicular to the shaft. It is perpendicular to the shaft. VW1 is the tangential component. If I draw a circle like this, then VW1 will be the tangent. Suppose if I have to find out the VW1 at this point, then VW1 will be like this. It will be tangent. VW1 is the tangential component. Now VF1, VW1 and VA1 are perpendicular. VF1, VW1 and VA1 all are perpendicular to each other. Similarly, at the outlet, VA2 is the parallel to the axis of the shaft and VF2 is perpendicular to the shaft and it is the flow component, and VW2 is the tangential component at the outlet. So this is the general diagram for any rotodynamic machine, and it is, if I am assuming that this is a rotor, then all these are the component of velocity at the inlet and outlet. Now with the help of this diagram, we will derive the Euler equation, or we will find out the generalized equation for rotodynamic machine. You see here, this is the diagram which I explained in my previous slide. VA is the axial component, this one is the axial component, and if I say VA1, then it will be at the inlet. Now VW is the tangential component or wheel component. So VW for the inlet is VW1 and for the outlet that will be VW2. This will be the tangential component. VF, flow velocity, that is perpendicular to the shaft. VF1 for the inlet condition, please correct it, this one is VF1. This is VF1. This is for the inlet condition and this one is the for outlet condition. V is the absolute velocity. Now you know very well what is torque. Torque is the force multiplied by perpendicular distance. Now in this case, what is force? In this case, the force is mass flow rate into velocity and perpendicular distance is r, because this if this is the inlet point, then the distance between the axis of the shaft and to this point is r1. It is a circle, you have to remember this. This one is making a circle. Since it is a two-dimensional diagram, then that's why you are not able to understand. You see in this diagram, if I say this one is r1, this one is r1, okay, and in this case you see here this one is r2. Now what is the torque at the inlet? Torque at the inlet is force multiplied by perpendicular distance. And what is force? Force is the mass flow rate into velocity. And which velocity is giving the torque? The velocity, this velocity, if I say this velocity VW1, VW1 is giving the rotating effect for this rotor. VW1 is giving the rotating effect to this rotor. That's why the velocity component VW1 will be used to calculate the torque at the inlet. So m dot into VW1 into R1. Similarly, at the outlet we can write m dot into VW2 into R2. Apply the momentum theorem, or we can say change in momentum. The change in momentum, that means final momentum minus initial momentum. So torque will be equal to m dot into VW2 R2 minus VR1. Now we have calculated the torque. Now what is the rate of energy transfer? Rate of energy transfer, or you can say power. Power is equal to torque into omega. This is the torque into omega is the rate of energy change in the fluid. That means if I multiply this equation with omega, this is the omega, and if I multiply this equation with omega, then I'll get power is equal to m dot into Vw2 U2 minus Vw1 U1, because U is equal to R omega. You know very well U is equal to R omega. So for the outlet condition, value will be R2 into omega, and for the inlet condition it will be R1 omega, and I have replaced R2 omega with U2 and R1 omega with U1. So this is the power or rate of energy transfer in this case. So this one is the rate of energy transfer imparted on vane or rotor by the jet. Now this is the equation we calculate. This is the power or rate of energy change in the fluid. Now per unit mass, this will be equation Vw1 U1 minus Vw2 U2. Now if I calculate the rate of energy transfer per unit weight, then I'll get 1 by G into Vw1 U1 minus Vw2 U2. That means head. Now this is in terms of head. This equation is in terms of head. Now this is the Euler equation in terms of head, and this one is the first term and this one is the second term. If you see here, Vw1 U1 is greater than Vw2 U2, then this one is positive. So this one is the equation for the turbine. This one is the equation for the turbine. Now if Vw2 U2 is greater than Vw1 U1, then this equation will become for the pump or compressor. Okay, let's see. When Vw1 U1 is greater than Vw2 U2, then this equation will be for turbine. When Vw2 U2 is greater than Vw1 U1, then this equation will be for compressor. Okay. Now let's see the Euler equation in terms of component of energy transfer. Considering the inlet velocity triangle and outlet velocity triangle, you see the inlet velocity triangle, this inlet velocity triangle I'll use, and this outlet velocity triangle I will use to calculate the value of Vw1 U1 and Vw2 U2. Friend, this is not in your syllabus. You have to just remember this thing, and this formula you have to remember. How this formula is derived, it is not in your syllabus. You just have to remember this formula, and this formula you have to remember. This is not the part of your syllabus. Just I have given you that how we have reached here. Okay. So with the help of inlet velocity triangle and outlet velocity triangle, we got the values Vw1 U1 is equal to half U1 square plus V1 square minus VR1 square. Similarly, for the outlet velocity triangle, we got the value of Vw2 U2 is equal to half U2 square plus V2 square minus VR2 square. This is the base. This is basically the equation which we got from the vector. You know very well vector, and you have studied in your school time. Okay. Now I put the value of Vw1 and Vw2 in this equation. Then I'll got the value 1 by G into half into U1 square plus V1 square minus VR1 square minus half U2 square plus V2 square minus VR2 square. If I solve this equation, I'll get this value. This is the energy transfer to the rotor of a fluid machine by the fluid machine. This is in terms of weight or in terms of head. We can say this is the energy transfer in terms of head, or this is the energy transfer per unit weight. You have to remember this thing. Okay. Now if I write this equation like this, H is equal to 1 by 2G V1 square minus V2 square plus 1 by 2G U1 square minus U2 square plus 1 by 2G VR2 square minus VR1 square. This is first term, this is second term, and this one is the third term. Now I'll explain what is first term, what is second term, and what is third term. Now this is the first term, 1 by 2G V1 square minus V2 square. You know very well this is the change in velocity head. This is the change in velocity head, or you can say it is change in kinetic head. This is change in velocity head or kinetic head. This is per unit weight, or you can say it is in terms of head. Okay. Now second term is 1 by 2g u1 square minus u2 square. This is change in head due to change in its position. This is the change in head due to change in its position. You know very well u is equal to r omega, and for the inlet condition u1 will be equal to r1 into omega, and u2 is equal to r2 into omega. You see r1 and r2, that means it is the position of the fluid is changing at the inlet and it is changing at the outlet. That means its position is changing. Because of change in position, this will give centrifugal head also. This is called centrifugal head also. Okay. Now let's see the third term. Third term is 1 by 2g vr2 square minus vr1 square. This is called the relative velocity head. You know very well what is the relative velocity. Relative velocity is v1 minus u1, that is vr1, and what is vr2? Vr2 is equal to v2 minus u. Okay, if vane is fixed, that means vane is not moving, then what will happen? Vr1 will be equal to v1 and vr2 will be equal to v2. You see here that vr1 is now dependent on v1 and vr2 is dependent on v2. Now v1 and v2, that means from the inlet up to the outlet, the velocity is changing. From the inlet to the outlet, velocity is changing. Okay. Now why this velocity is changing? This velocity is changing due to the friction on the vane, and flow area changes, and the flow area of the vane is changing. That's why the velocity will change from v1 to v2. Now what is the flow area changing? What is the meaning of this term? You see here, as the area will change, the velocity will change. Suppose it is a nozzle, then in nozzle what will happen? Area will change. If area is changing, then suppose it is a converging nozzle or converging duct, then area is decreasing, then velocity will increase. Okay, if velocity will increase, then pressure will decrease, then pressure will decrease. So similarly, in this case, the space between the vanes is made like a converging duct. The space between the vane is like a converging duct. So in this case, the velocity is increasing. That means velocity is increasing from the inlet to the outlet. Or if velocity is increasing, that means kinetic energy is increasing. If kinetic energy is increasing, then pressure energy is decreasing. If I consider at the inlet and outlet, the velocity at the outlet is more than the velocity at the inlet, then the pressure at the outlet is less and pressure at the inlet is more. So I can write P inlet is greater than P outlet. That means fluid releases its pressure or contributes or give away its pressure energy to the rotor. I think it is clear. The fluid releases its pressure or contributes or gives away its pressure energy to the rotor. That is, pressure at the inlet is more than the pressure at the outlet. If VR2 is greater than VR1, you have to remember pressure at the inlet is more than the pressure at the outlet. Okay, that's why this term is also giving the pressure head. This term is giving the pressure head. Now you see here 1 by 2g VR2 square minus VR1 square, we can write P1 minus P2 by 2g, and this term is nothing but the change in pressure energy or static head. Okay, so from the above discussion we can say that second term and third term both contributes to the energy transfer of the fluid machine in terms of static head. Okay, and these are the Euler equation. These are the Euler equation in terms of, this is the rate of energy transfer and this is the rate of energy transfer per unit mass. This one is the rate of energy transfer per unit weight, or in the terms of head we can say. All these equations I have explained. Now you see here, the above equation is for turbine. This equation is for turbine. This one is for turbine and this one is for turbine. This one is for turbine. In this case, if VW1 U1 is greater than VW2 U2, then it is for turbine. If it reverse, That means VW2 is VW2 U2 is greater than VW1 U1, then it is for pump or compressor. Or in general, if I say if all above equation is multiplied by -1, then these equation will be for pump and compressor. So friends, in this video, we have studied about the Euler equation and how the Euler equation is derived. All these things we have studied in this lecture. In the next lecture, we will study about the type of hydraulic turbine. There are different type of turbines which are classified based on head, based on speed, based on the principle of operation. All these classification we will study in the next lecture. Thanks for watching this video and have a good day. Bye bye.